Dear students, I am Samir Velankar. I welcome all of you to this next video on graph data structure. In the previous video, we saw an recursive algorithm for DFS, depth first search algorithm. In this video, we will be looking at BFS algorithm. Now, BFS algorithm inherently is non-recursive, although we can write recursive method for BFS. But ideally, BFS is written as non-recursive algorithm and it uses queue data structure. We first start whenever we write any algorithm, it's a good practice to write comments. In the comments, we write what is given to us and what we are supposed to find. And are we going to use any additional data structures, any variables? All these things are written descriptively in the comments. So what are we given? We are given a graph, any graph, it can be directed or undirected, which has V vertices and E edges. So as an example, we have a graph here which has 6 vertices as you see, and some number of edges. I am not counting edges. So there are E edges. So we have V equal to 6 in our example. V is 6 number of vertices and some number of edges we have. Now we assume that this graph is already stored in the form of adjacency matrix G. Now you recall a graph can be stored in two methods, adjacency matrix or adjacency list. We are assuming that the graph is stored in the form of matrix. So the algorithm that is mentioned here uses the matrix G. Clearly, G matrix stores the adjacency of the graph. So for this given graph, the adjacency matrix will be definitely 6 by 6. It will contain 6 rows and the elements of the matrix will be filled either with 1 or 0 depending on the adjacency. So in the previous video, we saw the same graph and we filled adjacency as shown. I don't find any sense in discussing why these elements are with 0 or 1. We very well know this. How these elements have been filled. Oh, I am so sorry. This second row will be 2 to 1 is 1, 2 to 2 is 0, 3 should be 1. So sorry. Because 2 is adjacent. 2 to 4 is also 2 to 4 is also 1. Is adjacent to 4. As you see, there is an edge from 2 to 4. 2 to 5 is also 1, but 2 to 6 is 0. 3 to 1 is 0, 3 to 2 is 1, 3 to 2 is of course 0, 3 to 4 is 1, 3 to 5 is 0, 3 to 6 is 1. By the way, 4 to 1 is 0, 4 to 2 is 1, 4 to 3 is 1, 4 to 4 is 1, 4 to 6 is 1. 2 more rows to go, 5 to 1 is 1, 5 to 2 is 1, 5 to 3 is 0, 5 to 4 is 1, 5 to 5 is 0, 5 to 6 is 1. And finally 6 to 1 is 0, 6 to 2 is 0, 6 to 3 is 1, 6 to 4 is 1, 6 to 5 is 1, 6 to 6 is 0. So we assume that this matrix G is already created for this graph. And what else we have? The algorithm uses an array named as visited, just as in the case of DFS. And that visited array has V elements, and all the elements of visited are initialized to 0. So, this example, we are exactly having a visited array, and the visited array is going to have 6 elements. So there are 6 vertices, and all those elements are 0. From the earlier discussion of BFS, you know that visited array will be used as a flag, and it will indicate whether a particular vertex is visited or not. 0 means the vertex is not visited, 1 means it is visited. Vertex is visited. Okay, what else we have? Other thing we have in the comment here is the algorithm also uses a queue data structure, first in first out data structure, FIFO data structure. queue stores the vertices which are marked as visited, and the queue is initially empty, you see. So I often draw a queue on the paper as we have a queue named as queue, and this queue is drawn by me as follows. This is an empty queue. Now, anyone joining this queue will join from here. So, any person joining will join at this end, rear end, and the people will come out from this end. And you know all the properties of first in, first out, how it works and all that. All right. And the last thing in the comment written is the algorithm is invoked from main procedure or main program as BFS1. So what we mean by this is that BFS algorithm will commence or begin from first vertex. So let's start discussing BFS. BFS algorithm has a parameter k where k is 1 initially, isn't it? Because we passed the parameter 1. That's how the BFS was invoked from main procedure. So we mean that BFS is going to commence from the first vertex. So what was the procedure? We print 1, recall, we mark 1 as visited, and then we see the neighbors of 1, and we print all the neighbors in increasing order. Check the video we made separately for the procedure of BFS. So if BFS has begun from 1, let's see what happens next. We insert the kth vertex, that is first vertex, k is 1, in the queue. That's the insert function of the queue data structure. What are we inserting is the value of k, which is 1, in the queue. And remember, the queue was empty initially. Now the queue shown here is now going to store 1. So the queue is no more empty. It was the initial vertex from where we started has been inserted in the queue. The next line, after inserting initial vertex k in the queue, we mark that kth vertex as visited, that is 1. So visited 1, remember k is 1, visited 1 becomes 1. Hence, the first element of visited has been marked as 1. So in the picture, we are going to tick vertex 1. Surprised everyone, you should be. Because we know that we tick a vertex, we mark a vertex as visited only after printing it. But actually vertex 1 has not yet got printed. Yes, we have not executed print statement on vertex 1. So how are we ticking it? How are you marking it as visited? The BFS algorithm we have written is such that whenever a vertex is inserted in the queue, we will immediately mark it as visited. I repeat, whenever a vertex, any vertex is inserted in the queue, note it is not yet printed, it is only inserted in the queue, we will immediately mark that vertex as visited. You will know the reason shortly. Okay, so we have finished with insert initial vertex in the queue. We have finished with mark that vertex as visited, and now the whole entire thing, entire BFS is controlled by the while loop. This while, as you see, will continue as long as queue is not empty. So the while will break when the queue becomes empty. Notice that queue is not empty at the moment. It was empty, but we inserted initial vertex k in the queue. So now the queue is not empty, hence the while will continue. So now you might understand how important the line was. Insert the initial vertex. If we did not insert this, then the queue would remain empty and the while will straight away break, isn't it? So it's a good idea to force the queue not to be empty, insert the initial vertex. Now the queue is not empty, while loop is. Let's go into the while loop. All right. So what's the while going to say? Queue is not empty, so enter the while. And immediately call delete function on the queue. Now you know whenever you call delete function will always delete first element of the queue. This is not delete entire queue. That's very funny. Delete queue means delete the frontmost element of the queue. And you observe the queue. The frontmost element of the queue is 1. So 1 gets deleted. And the value deleted from the queue is silently stored in K. So K is 1. Because the deleted value from the queue was 1, K is 1. Very funny, isn't it? K was 1, we inserted 1, we deleted 1, and we are storing that 1 in K again. Very funny. But you will see the colors of this particular statement, delete Q, and what it does during next repetition. So anyway, by the way, at the moment K was 1, it remains 1. We inserted 1, we deleted 1, we are again putting it into K. Now the next line, we print K. So 1 gets printed. Remember, vertex 1 is already visited. It is already checked as visited. See the visited array. Okay, so 1 has got printed. Now what? After printing any vertex, we will check the adjacent vertices of that. Isn't it so? So how do you know who are adjacent to vertex K? Remember K is 1. You just be in the first row of the matrix and see all columns in this row. And whichever columns have entry 1, that column number is the vertex which is adjacent to 1. So who are adjacent to 1? Vertex 2 is adjacent because column 2 is having 1. Vertex 5 is adjacent because column 5 is having 1 in row 1. So to do this, we will keep the row number as k. K is 1, remember. And column number will be varied from 1 to 6. I know you will hate listening all this explanation if you have carefully gone through DFS. Just go through this. Every word which I spell out. Okay, so we start the loop with I equal to 1. With I equal to 1, we are going to see what is G11 because K is 1 at the moment and I is 1. Is it 1? But G11 is 0. What that means is vertex 1 is not adjacent to vertex 1. So the very first condition in the if is false and we have used AND, which is logical and you know the property. If the first condition itself is false, the entire if is false. So none of the lines written in the if will run and we will go back to for. So for is now going to make I equal to 2. When I is 2, we will see whether second vertex, because k is 2, sorry, I'm so sorry. First vertex, k is 1, is it adjacent to second vertex, I is 2. So we are checking G12. Notice that we are in the same row and we have moved on to the second column. So I is 2 now and it is 1. So what we observe is first vertex, kth vertex is adjacent to second vertex, ith vertex because the entry is 1. And also that second vertex, that is ith vertex, is not marked as 1 in the visited array. Observe the second element of visited. So second vertex, come back to the picture of the graph, is adjacent to 1 and second vertex is not yet ticked. So second vertex is an ideal candidate to be processed. But what we do is, as both conditions are true, observe, both the conditions are true, we don't directly print it, but we insert that 2. Observe the statement. We insert that I. So I is 2 at the moment. So 2 will get inserted in the queue. And after inserting 2 in the queue, we will immediately mark that second vertex, second element of visited will be marked as 1. I said early in this discussion that we mark a vertex visited immediately when that vertex joins the queue. All right then. By the way, you always remember what is K. K is 1. And what was I? I was 1, but nothing happened when I is 1. Because 1 comma 1 entry in the matrix is 0. But when I is 2, 1 comma 2 entry, first row, second column is definitely 1. And second vertex was not visited. So 2 got inserted in the queue. Now go back to the for loop. I will become 3. Check the entry 1, 3. The entry we are checking is ki, that is 1 3. You notice in the matrix 1 3 0. Also in the picture you see 1 and 3 are not at all adjacent. So we are not at all interested in that entry. If is false, and we go back to for. Now you can make in the for, you can make I as 4, and you observe 1 and 4 are also not adjacent. You then go back to for and make I as 5, and you see 1 comma 5, first row and fifth column, kth row and ith column are storing 1, and also and you see visited of 5, fifth element of visited is not 1. Yes, fifth element you see is not 1. So we see that 1 is adjacent to 5 and 5 is not visited. As both these conditions in the if are true, we will insert ith vertex. Ith vertex inserted in the queue means 5 will get inserted in the queue. And you know, whenever any vertex joins the queue, we will immediately mark that vertex as visited. So visited 5 is immediately made 1. So the fifth element of the visited is made 1. In short, in short, we are claiming that fifth vertex is ticked. All right. So where were we? I was 5. Now let's go back to the for and make I as 6. So we are now checking first row sixth column, kth row ith column, and as you see, first row sixth column is 0. So the condition of adjacency fails. Now after reaching I is equal to 1 to 6, most importantly the for loop ends. Note that we were hanging in this for loop going through all columns 1 to 6. Check the for loop took us through all columns 1 to 6 in the row 1. We have now finished with the for loop, isn't it? So obviously we will be back in the while. Check the cursor place. That means we will go back to the while and inquire, can we repeat? Remember, we can repeat only if queue is not empty. And you observe the cursor place here on the queue. Queue is genuinely not empty. In fact, it has two values. So time to enter the while loop again. This time the while is repeating second time. The first statement in the while loop is delete queue. So it will delete the frontmost element of the queue and store the value k. So notice the frontmost element of the queue this time is 2. So 2 gets deleted and k stores the value of the deleted element. So now the new value of k was 1 earlier, but the new value of k is now equal to 2. I hope you are getting it. Now why suddenly we have made k as 2 is because we are going to print that 2 now. 2 was already marked as visited. Sorry, I forgot. It was marked as visited. So we have deleted 2 from the queue and the next line is print 2, isn't it? Because k is 2. So the output by this time is 1 was printed and 2 is printed. Now after printing 2, we will see who are adjacent to second vertex. Note the queue diagram. 2 is no more in the queue, but whoever is adjacent to 2 will join the queue now so that they can be later processed later. So how do you see who are adjacent to 2? It's very easy now. All of you know it very well. We want to know which vertices are adjacent vertices of second vertex. Then you will just keep yourselves in the second row, isn't it? Be in the second row and visit all columns in the second row. It is so easy. I hope you are understanding. So the second row is what we target now. K is 2 and we move on all columns. So let's start this for loop all over again. With I equal to 1 now, when k is 2, we will check g ki. Check the if statement. If g kth row ith column, that is second row first column, is it storing 1? Yes, second row first column is storing 1. Check the matrix. That means second vertex is adjacent to first vertex. But that's not enough, isn't it? Adjacency is not enough. You tell me while processing 2, will you consider 1? No, no, because 1 is already visited. You won't consider it. So the second condition comes to our rescue. It says although 2 is adjacent to 1, but first vertex, I is 1, first vertex is already marked as 1. So not equal to 1 is false. You can see that the first vertex is already marked as 1. So the if becomes false and we won't insert 1 again in the queue, it would have been havoc. If you would say that 2 is adjacent to 1 and we will insert 1 again, then 1 will be deleted again and 1 will be printed twice. So nothing happened when I was 1 in the for loop. Now I repeats with I equal to 2. So obviously we are going to check second row, second column, kth row, ith column, which is 0. So forget it. I is 3. Second row, third column, check second row, third column is 1, isn't it? And you very well see the graph. Vertex 2 is adjacent to vertex 3. And see the second condition written after and, logical and, visited 3, because I is 3 now, is really not 1. Yeah, visited 3 is not 1, true condition. So the if is true, hence we insert that ith vertex in the queue. So ith vertex visit inserted in the queue means now 3 will get inserted in the queue. And as soon as we insert that third vertex in the queue, we will mark that third vertex as visited. Marking third vertex as visited means that we have already ticked this vertex. All right. Let's go back to for and make I equal to 4. Is 2 and 4 adjacent? Oh yes, very well. And is 4 not visited? Yes, 4 is not marked as visited, not marked as 1. So we go inside the if and we insert fourth vertex in the queue and mark fourth vertex as visited. So it is in the queue. Fourth vertex is in the queue. So we will mark it as visited. Let's go back to for and make I as 5. Is k and I adjacent? Is 2 and 5 adjacent? You can see that 2 and 5 are also adjacent. But 5, vertex 5, is already marked as visited. So we'll not commit a mistake of putting 5 again in the queue. Then I is 6. 2 and 6 are not adjacent itself. So the first condition of the if itself fails. So 6 is not inserted in the queue. And what you observe again is the for loop over here ends because it has gone from 1 to b to the entirety. So if the for ends, if the for loop ends, the while continues. And while will continue because queue is not empty. Note that not empty queue is true because queue contains 3 values, 5, 3 and 4. So now let's see the summary instead of going through line after line. What will happen when the while continues? Delete the frontmost element and give it to k. So now k will become 5. After making k as 5, you print k. That's the next line. So up till now the outputs go to BFS were 1, 2 and 5. And remember 5 is already marked as visited. Check the visited 5 element. It is 1. Now you will see adjacent or neighbors of 5. So you will start the for loop as you see the next statement in the algorithm. You will start I with 1 all over and check 5 comma 1, fifth row first column. It is 1, meaning 5 is adjacent to 1, but 1 is already visited. So second condition fails in the if. Then make I as 2. 5 and 2 are also adjacent, but 2 is already visited, so forget it. 5 and 3. 5 and 3 are not adjacent itself. So make I as 4. 5 and 4 are adjacent, but 4 is already visited. Then make I as 5, but 5, 5 is never adjacent, isn't it? Then 5 and 6, and you see fifth vertex, that is kth vertex, is adjacent to ith vertex, that is sixth vertex, and sixth vertex is not visited. So we will put 6 in the queue. Check the if. If the if is true, then we insert I in the queue and we also mark that element of visited, that is sixth element, as 1. So sixth vertex is marked as visited. You can observe that the loop, has gone entirely from 1 to B. So the loop ends, the for loop ends, and the while continues. The while will continue, definitely, because queue is not empty. As queue is not empty, we will enter the while again and we will delete the frontmost. The frontmost this time is 3. So k becomes equal to deleted value. So k becomes 3 and we will print on the output. Now we will get 3. And remember, vertex 3 is already visited. It is checked as marked as visited. So let's find out adjacent vertices of 3. So we will go into the for loop again. The next line is the for with I equal to 1. Notice 3 and 1 are adjacent, but no, sorry, not adjacent only. Sorry. 3 and 1 are not adjacent. I is 2. 3, 2 are adjacent, but 2 is visited. So forget it. 3, 3 is not adjacent, isn't it? 3, 4. 3 and 4 are adjacent, but 4 is visited. So forget it. 3 and 5. 3 and 5 are not adjacent itself. 3 and 6. 3, 6 are adjacent, but 6 is visited. Observe how important it is to mark vertex 6 as visited, although it is not yet printed, but 6 is waiting in the queue. Observe 6 in the queue. So 3 has adjacency to 6, but it was so important that we marked 6 as visited, saying that okay, 6 is now in the queue. Wait. So if you find any other vertex which has adjacency to 6, just don't make a mistake of putting 6 again in the queue. By the way, the for k equal to 3 is over. By the way, 3 was such a vertex which did not put anything new in the queue, isn't it? Interesting. So the for is over and we will go back to while. While will repeat because queue is not empty. So 4 will get deleted and now k will become 4. So what happens when k is 4? We will print 4. That's the next line in the while loop, isn't it? And then we will start a loop to check the adjacent vertices of 4. But you will see as I goes from 1, 2, 3, 4, 5, 6, for none of these values of I, for none of these values will ever the if statement become true. Because either the vertices are not adjacent or vertex is already visited. So the loop again ends over here, isn't it? And we go back. For loop ends, so we go back to while. When the while goes in again, 6 is deleted from the queue. Now you see how the queue is becoming diminished. Queue is becoming empty. Rather, it has become empty. So we delete 6 and we give it to k. There is no room up there. So I am writing now k is 6 here. So on making k as 6, we will output 6. Just see the top of the board. We are printing 6. And what are we going to do? Start a loop all over to check the adjacent vertices of 6. But you very well know, I will run from 1 to 6, but no use. For none of these values of I will the if ever become true, because either the vertices are not adjacent to 6th vertex or they are already visited. So the for loop here ends again. And we try to go back to while and repeat it, but while won't repeat at all now, because the queue has become empty. You see, there is nothing pending in the queue. Observe the mouse hovering over here. The queue has entirely become empty. So there are no vertices waiting to get processed. And the queue is empty, so while loop will break and the algorithm will end. I hope you got enough from this discussion how exactly the BFS works. So just as a small recap before we end this video, just see, suppose I have a graph like this. Imagine some arbitrary graph I am drawing. This is the graph. Okay. So what are the steps of BFS on this particular algorithm? You know that queue is empty initially, and you know that the visited array, I'm just running BFS very fast, On this graph, very small graph, visited is going to have 5 elements, all elements initialized to 0, and Q is initially. We start with K equal to 1. BFS starts with K equal to 1, and we insert that 1 in the queue. That was the first statement in our procedure BFS. And whenever anything is inserted in the queue, we will mark that element of visited as 1. Now we see the neighbors of K. Neighbors of K are 2 and 3 in the graph. 2 and 3 are adjacent to 1 and they are not visited. So what are we going to do is, we are going to delete 1, we are going to print it, and we are going to insert 2 and 3. But inserting 2 and 3 in the queue means they are as good as visited. You tell me, if 2 and 3 are in the queue, isn't it that they are getting ready to get deleted, and after deleting they would get printed? So if 2 and 3 are in the queue, it's nice to mark them as visited. They are as good as visited, isn't it? So with K equal to 1, we have visited 2 and 3. Now when we go back in the while loop, the frontmost element is 2. So now make K as 2 here. And you print 2 and see who are neighbors of 2. Whoever are neighbors of 2 will be inserted in the queue. Now the neighbors of 2 you see are 1 is neighbor, and 4 is neighbor. But 1 is already visited. So only 4 will be inserted in the queue. And fourth vertex will be immediately marked as visited. Alright. Now we go back to while again and delete the frontmost, that is 3. Okay. That means K is now going to be 3. Oh, I forgot to mark 4 as checked because 4 is now visited. Now after deleting 3 from the queue, K is 3. And we will print that vertex 3 and see who are the neighbors of 3. Now neighbors of 3 are 1, 4, and 5. But among these neighbors, 1 and 4 are already visited. They are checked as 1. Only 5 is pending. So 5 will be inserted in the queue and 5 will be marked as visited and 5 will be checked. Now when we go back to while again, 4 is deleted, 4 is printed, but on checking who are the neighbors of 4, we don't get any new vertex, isn't it? So for 4, there is no new entry in the queue and we go back to while again. While loop will then delete 5 and print 5. But on after printing 5, when we check the neighbors of 5, there are no new neighbors which are yet to be visited, or everything is visited rather. So now when we go back to while, the queue is genuinely empty. You can check the queue is empty here. So the algorithm stops. By the way, before I end the video, I would like to tell you that such difficult procedures, or rather, this entire procedure will not be asked in the GATE exam because GATE is objective type. But my methodology, and rather any teacher's methodology to teach data structures or any programming topic is, I want the students to know the program. You should know the procedure in and out. Only then you can attempt the objective type questions within a few seconds. And believe me, if you are following these videos properly, patiently, and not fast forwarding it or playing with the controls given under the video, you will be successful and you will be really very, very comfortable solving the questions.